So let's go and see whether we can improve, have a cake and eat it too. Let's say we like some things of Lisp, and the one thing that was hard to defend was dynamic typing. Okay? And you might say that dynamic typing is a consequence of the fact that we didn't type the variables. And we don't want to type variables because we've got an interpreter and we're doing this interactively, and we don't know what we are doing because we're doing AI. And so we don't want to type the variables, and yet we want static typing. Have you guys seen this before? We know in Java you got to type the variable and you get static typing. In C that's the case. Or maybe not. Any other language you guys have studied? How many of you took Chris's 110? Did you? Was there any? Did you see a feature that is consistent with what we want? Did you have to type all the variables? You did? Really? He required you to do so, or you did it?
I did it when he was still teaching Java.
When he was doing Java?
Yeah.
Oh, you guys are that generation?
Yeah.
Good. So that was that generation. No, he changed to TypeScript. Yeah.
Auto in C, right?
Sorry, auto?
Yeah.
C.
Like the auto keyword, where you can declare a variable as auto interpret it, but you can also set it there.
And when you do it, I don't know TypeScript. So you're teaching me TypeScript here.
Like C++ is auto.
So when you do auto, what does it do?
Auto, it's as if it's a dynamic type where it inserts what type it is.
But do you get the errors at runtime, or do you get the errors at compile time?
I think you get it at runtime.
Did you do a TypeScript with him? But you know. Okay. So there is something called type inference, which also exists in Java right now for primitive variables declared within primitive local variables. So what we can do is I showed you that function, greater than equal to. Greater than equal to does not take strings as arguments. What's that greater than equal? Yeah, it doesn't take string as arguments. So we can infer that what is going to be passed to greater than equal to is going to be something that is comparable. Okay? And if the range of types is very small for an operator, we can infer the types. Okay? So we don't want dynamic type checking, we want static type checking. And so Java TypeScript type inference for local variables. Okay? So there's a term called type inference. Type inference got invented early 70s or maybe even earlier, but it's a hot new feature in Java. And TypeScript is also a hot new language compared to JavaScript. So you're seeing, again, back to the future concepts here. Okay? So this is not going to be all a set of irrelevant traditional concepts. Okay? So let's see it at work. We're going to use ML as an example, which I believe is the first language that did type inference, at least the first language I saw. And let me let you guys look at this code and see whether there's anything unintuitive here. All right. So on the top is what I typed, just like Lisp. On the top is what I put in a file. I got the formatting. On the bottom is what happened when I went and interacted, when I went and loaded the file. Not interacted. So is this making some sense? A little bit more intuitive syntax than Lisp. Right. So let's go line by line here. The very first thing I'm saying is not setQ. That's just a keyword. I'm saying val. Okay. I'm saying pass cutoff equals 60. Just as I said in Lisp. Setq pass cutoff 60, just a different syntax. As in Lisp, the very first line goes and evaluates, it tells you what you got instead. But what am I getting as the first line of output here? That's different semantically from what I saw in Lisp. The first line of output is val pass cutoff equals 60 colon int. Right? What did you see in Lisp? You just saw the value. So what's it telling you here? It's telling you I inferred that pass cutoff is an int, and I inferred that I'm going to make sure that everything you write after that is consistent with my inference. At compile time. Okay? Then you went and defined regular pass as a function. You said fun rather than val. Okay? And you said a regular pass is a function whose body is, which takes as an argument a total. Okay? And its body is what comes after equals. And the return value is a total greater than or equal to pass cutoff. Okay? Different syntax, but you see the keyword for function, you see parameter. Okay? It's not within parentheses. Okay? And that's allowed. If it's only one parameter, you don't have to define that within parentheses. And we'll see why it can do that. There's a conceptual, there's a concept there. And so we just say a total without parentheses, and we go and say a total greater than or equal to pass cutoff. And it says, oh, I have inferred that regular pass is a function, and what is and it takes as parameter a single int and returns a bool. Okay, how does it know that? It knows pass cutoff is int already. It knows greater than or equal to is defined in terms of ints, and it knows that if the right hand argument is an int, the left side of greater than or equal to is also must be int. So it's figured out that a total is an int. And once it knows what the result, and so it knows also that greater than or equal to will return a Boolean. So it says, okay, I know enough context to say that it's a function that goes from an int to a bool. Okay, so it's inferring the type. After that, there's nothing new. It goes and defines. It gives you the values of the expressions, and these values are either functions here or not functions. Okay. Make sense? There is something confusing here, though. Look at the names I use for the named constants. What's the problem? Sorry? A little louder. I have two named constants with the same name. That is not very good naming, but I wanted to show you a feature in ML. So when there are two names, it allows that. So there seems to be an ambiguity here. Which value should I use? So can you guys figure out a way to resolve the ambiguity? Yeah.
I have a question. Did it just store the value when you define the function? Did it just store the actual value, not the variable, so that you can reuse the variable name?
So you can always reuse variable name, but I have two values associated with it. So I have two choices. Either I use the latest value, or I you use the one that was most recent, the one corresponds to the function you're calling. So there are multiple versions of this value. The first version is used in regular pass. The second version is used in high finite pass. You don't like that? So it's probably going to be confusing, but there are basically multiple versions. Okay, just as in Java, I can have a superclass have a variable called n, and I can have a subclass have a variable called n, and different methods refer to the methods in the subclass refer to the subclass n, and the methods in the superclass refer to the superclass n. I hate this feature because I can't tell you how many times I've been bitten by this. You refactor code, and you go and put all the methods on the superclass, but you forget to take out the variable name, and then you get bit. And there's in fact some style checks you can do to make sure that doesn't happen. But it is a conceptual possibility, and we have seen that Milner, who's the guy who invented ML, explored this possibility. Okay? So each expression automatically typed, we see this, and so we see this, and we have two the same name used twice. So new version reference by later code, previous versions reference first version. Okay. And then I can call this function, and nothing, and when we call, there's a return value. The return value is called it. Okay. So it's telling you that the answer is false, and by the way, false is a Boolean. Okay. And it says that for all the various values we have. So this is how ML is used. Okay. Questions? So you can see going from list to ML, syntactic, most of the concepts got reused. There were a few things that we had to learn because it was static type. Okay. So you guys are getting restless because there's only 30 seconds left. By the way, let's just finish this off. So can you guys see a disadvantage of type inference? Yeah. It would be more confusing to read the code. So you as a programmer have to go and figure out what the person did. Okay, when you evaluate it, of course, the interpreter will tell you what happened. But at declaring time, you provided less information. So there's possibility of that problem. So, but it's great for small, non-reusable scripts that are written interactively, that you get the benefit of type checking, and you don't have to type a lot. Okay. Okay. And another point is that, and I'll review this next time, that we are seeing that ML does more for the programmer. So the programmer can type less because the ML did more for you. You don't have to go and type the type, and the ML did more. And when we go to Prolog, we will see that idea is carried even further. Okay. And we'll see how. So what we'll do in each class is review the important things done in the previous class. That's a good thing to do anyway. But since I'm teaching this for the first time, the first time I present something probably wouldn't be the best way to present. So a second time is always good. Okay. And so the big thing, we spent most of last time reviewing what we had done the time before that, because there was a lot of material covered the time before that. But the main new concepts we saw last time were lambda expressions in Lisp. Okay. And we saw that we can define a lambda expression and apply it. And we also, and I did lambda, the Lisp code in a little bit more convoluted way than I needed to, because I wanted to introduce cond. But you really didn't need a cond. Often Boolean expressions are a good substitute for if-then else's. Okay, so this time I did it without cond, and it's shorter, and it makes the lambda expression clearer. Okay, so again, a lambda expression consists of, it's just a block of code, which is not named, okay, but it's like a function otherwise, which takes a parameter. And I've defined in the lambda expression the total parameter, and I've defined in the body of the expression what to do with the total and what value to return. So then I've got the lambda expression, and I'm applying, what do I do with the lambda expression? I can pass it to another function, or I can just apply it right there. Okay, so I didn't have to think of a name, which means, because thinking of a name always takes time. And I give the argument 49 to the lambda expression, and then I tell Lisp to evaluate the whole thing that I wrote, the fragment I coded, which is the application of the lambda expression. So the application of the lambda expression is nil here, okay, because 49 does not pass. So, like I said, the word lambda expression occurs in Java too, so this is the root of lambda expressions. And Java lambda expressions are more limited than this, and so you can sort of see the full power in this. Okay, so questions about lambda expressions? This is still overview, so we're going to go in depth in how to even implement these later. And it's a tricky thing, how much to do in overview, how much to do in depth. And it won't really be in depth because we're not studying Lisp, we're studying programming languages. So I'm just trying to give you a flavor so that you know what to expect in the assignments and what to expect in the course. Yeah.
Yeah, so with this particular Lambda expression, is there really any difference between this and like a function call with a hard-coded parameter?
So a function call with a hard-coded parameter, you would have had to, no. So this is a function declaration and a call combined together.
Okay.
So like I said, Lambda expressions are unnamed function definitions. And if you don't name them, what do you do with them? Because you can't refer to them later. So you can, with the declaration, provide the argument, which is what I've done. That's a simple use. But like I keep saying, you can define a Lambda expression and it passes a parameter to another function. Functions that take other functions or arguments are called higher order functions. Okay? So we'll see that concept in more depth when we look at ML or maybe even at Lisp. Okay, so there's very little motivation here if you're willing to name things. But if you're not willing to name things, this is great. Okay? So it's just that. So just focus on what they do rather than why they're important. Okay? We'll see that later. Maybe they're not important. Okay? In Java, we've been dealing with Java without Lambda expressions just fine. Or maybe not. So it's just a usability thing. Okay? Happy? Okay. And what's nice about introducing Lambda expressions is that the block of code itself is an expression. Okay, you can actually take that block of code and not apply it. In fact, you can assign it to a variable. Okay, and you can think of a function definition as just being an assignment of a Lambda expression to a name, and that name you can call later. Okay, and so the whole idea of Lisp, which is very for want of a better word, very beautiful, is that there is a duality. The distinction between data structure and code is very thin. Okay, there's a fine line. In Java, there is data structures, there is code, and you can't just take an array and convert that into a code. Okay, whereas here you can take a list and convert that into code if that list happens to be a Lambda expression. Okay, and Java will automatically evaluate a Lambda expression based on context, and you can ask it, and when it doesn't have enough context and you want to evaluate it, you can call the eval function on a Lambda expression and say, hey, this list that I just gave you, please evaluate it. And when it wants to evaluate something as code, as something that returns a value, you can say, hey, enclose that in quote, either the tick mark or the quote mark as mentioned last time, or within a list that contains the function named quote. And it'll try to evaluate that, and quote will say, hey, I'll just give you back what my second element is. And so there's a notion of sort of, as programmer, not making Lisp evaluate things where it wants to evaluate, and asking it to evaluate when you want it to evaluate. Okay? So the quote function basically is used when you want it to not evaluate something, and the eval function is used when you want it to evaluate something. And these two functions are going to be the first two things that you will implement in your assignment. So I'm kind of referencing them here. So that's one big concept. Okay, now in Java, by the way, I can take a piece of text and compile it and load it at runtime. I do that actually in the code I've built. Okay, but that's not as elegant as this, where you just take a list and say eval, and suddenly evaluate it as a code. Okay. So I see some puzzled looks on the faces. That's fine, because we'll study this in depth later. But just want to give you an intuition that there's a notion of taking that everything is a list. A function call is a list. That's why we use the prefix operation. Okay, and a list is anything within parentheses with elements in between. And we'll see the definition of list also in more rigor later. Okay, this is we did last time. I'm just reviewing. And like I said, I'm just giving you a basic feeling of what you're going to get. Okay. And then we saw that another sort of peculiarity was that we could get runtime errors. Okay, so I've defined regular pass as something that compares the parameter with pass cutoff. In Lisp, you can't actually compare strings, and we see here that pass cutoff is a string. But Lisp doesn't do any checking when you define regular pass. It delays everything till runtime. And when you delay everything till runtime, you might get an error, and so you get an error. And I confused you guys a bit or maybe a lot by mentioning C at this point and talking of core dumps. So C is actually a statically typed language. And we can get errors that are as irritating, if not more, as those you get from Lisp. Okay? And the reason you get those errors is because C is a weakly typed language. You can't ascribe a unique type to a variable. Okay? So if I go and say char star prompt, I could be pointing to a character, a single character. I could be pointing to a string, and that pointer is a pointer to the first character in the string. Or I could be pointing to an array, which is not a null terminated string. All three things are valid. And C says, well, whatever you do, we'll accept it. And if what you do is inconsistent with what you wanted to do, you'll get a runtime error, which is an error that is arising because of lack of typing. Okay, and you probably won't get any message other than, hey, something will fail in your code. Okay? If you're lucky. If you're unlucky, the pointer will go outside your address space. And it'll say, I can't go here because I'm going into the address space. The operating system will catch that. And you'll get sort of an error saying, something very bad happened, here's the dump of your memory, and figure out. Okay? Yes?
So you say there is a kind of a pointer is a void star.
Sorry?
Void star. Void pointer. Without dynamic hyphen or...
Yeah, I don't know what void star means. Anybody know what the void star means? Yeah, go ahead.
You talked about a pointer to void, which is like a little bit like a typeless pointer. You can cast it back and forth, but it's unsafe.
But in C, you really don't need to cast anything. It'll accept anything. But maybe there are tools like lint, which will actually do some checking. So maybe that is to really avoid any kind of checking. So void is more in the spirit then, where it can do anything, it can point to anything, and it'll cause even more errors. Okay, at least we know this is one of three alternatives: a character pointer, a string alternative pointer, and an array pointer. From what I'm understanding, you guys are saying, I've never used void star. It's a pointer to anything, which will cause even more problems. Okay. Again, we'll study weak typing in more depth later. This is just a teaser. Okay. So why did we have dynamic type checking in Lisp? Because it's an interpretive language, and we don't want to have to declare types, when we're typing interactively. So could we have our cake and eat it too? Could we not have to type the name, enter the type names, and yet have static type checking? And that's a question that Robert Milner, who invented ML, tried to answer. And he invented ML. And he invented the notion of type inference. And type inference is something. So, we'll talk about this a little bit more formally later. We did it at the beginning. Why study programming languages? It's like studying Latin. It'll allow you, you figure out English better, and you're more educated, and you can talk better with your peers and be more impressive. Or you can learn, you can learn new things. Or you can see things that will come in the future. So we are learning new things, and we're also seeing things that came in the future. So type inference is an idea that was invented in the early 70s, and people who built practical languages kind of ignored it, and now they're not. Okay, just like Lambda expressions. So we actually see type inference as a new feature in Java. It came with Lambda expressions. In fact, Lambda expression return value is not typed. It's inferred. So by studying the roots, you also study the full power in a functional language, and you study also the limited introduction in practical languages. Okay. So how does that go? Here's a concrete example. As in Lisp, we have not declared any types, and then you see at the bottom what Lisp did with what we entered. everything we entered it tried to type, and it said, you just typed pass cutoff, but I know that 60 happens to be an int, so I have decided that pass cutoff will be an int. Okay? And another quirk we saw was that you could declare the same variable multiple times, and we created multiple versions of the variable. Okay, much as you would see in Git. Okay? So the whole notion of this is a language with versioning, which is kind of cool. And when I say cool, I mean that it makes you think. Okay, maybe it's not the right thing to put in a practical language, but at least you know there was this alternative that had some pros and maybe more cons than pros, and that's why it's not in the language. Okay, so you get to understand better why what you see in practical languages. When I say practical, I'll say used. Okay, it's not that these languages are not practical. No one gave them a chance, perhaps. Okay. So we saw type inference. Okay. And with type inference, we should not get dynamic errors. So let's go and introduce a dynamic error. Let me make the second pass cutoff be a string 40. And then I can enter the high final pass that uses the second pass cutoff. And when I ask ML to compile it, yes. Two questions simultaneously. Something must be really bad here.
But okay, so you have pass cutoff done twice, right? And last class you said that it'll use like the one that's the latest call to it. So then why?
No.
No.
The latest previous call to it.
The latest previous call to it.
So the first regular pass on top, it might have had multiple definitions of high pass pass cutoff before that.
Okay.
It'll take the latest version at that point.
At that point. Okay.
When regular pass was defined, not when regular pass was called.
Oh, so when it's defined, that's the version it takes.
Yes. Good question. And high final pass takes the one that was defined before it. Okay, but it's not as if there's only one slot for high final pass. So in fact, you guys in your Lisp interpreter will create these slots. You build tables. So you won't be actually associating variables with addresses. Since you're doing an interpretive language, you just build a hash table. And each variable or identifier will have properties, and one of the properties will be a value. So with ML, you create multiple versions. So when you have scopes, what happens is when a new scope is introduced, you override the previous one, right? When the scope is closed, you finish. But in the global scope, you have only one version. Here, the global scope has multiple versions. They're equal. It's not that this is a more recent one, this is a more, and we'll pop it off. It's just two competing ones. Okay? Nathan.
Sort of with that, I'm thinking about how it would be implemented. When you define function regular pass, does it say pass cutoff? It doesn't look it looks in the memory at that time at where pass cutoff is, and it finds 60, and then it takes the number 60, and now that number 60 is forever in that code. So no matter if I change pass cutoff later, the function regular pass is a total less than or equal to 60.
So, indeed, every variable is a constant in functional languages, ideally. There is no such thing as changing of the value of a variable. Okay, single assignment, and this is in the spirit of that. Okay, and what it will really probably do is, since you'll refer to high final pass multiple times, it will build in the table a high pass final pass version 1, and so it is 60 with that. So that every time you refer to it, it looks at that up and uses 60. But that will never be redefined. So you know how there's immutable strings in Java, which makes Java's life much simpler, much better, more efficient? There's notion of immutable variables, which are like really final constants. In a pure functional language, variables are just identifiers for values, and you don't change them. Okay. Robert? Okay. And I'm glad you're thinking implementation, because this course is going to be oriented towards that, rather than use of these languages, implementation of the languages. Other questions? Okay, so now I did something bad. The second version of pass cutoff is a string, and when that is used in my high final pass, it's being used as an int. So when high final pass is processed, Not when high final pass is called, but when high final pass is processed, I should get an error. Okay? And what I'm using here is an Eclipse plugin, which will let you enter the code, but it doesn't go and compile the code incrementally. It compiles the code when you ask it to. That's why I didn't get any errors as Eclipse or IntelliJ would give you. And we see here this inconsistency. So this is a type error, which would be allowed in Lisp, but before, when the compiler gets into action, it says, sorry, there's a type problem, fix it. Okay. So we look a little bit at the type inference algorithm also when we study ML. Okay. And we'll be, in the extra credit, we'll be using ML to write an interpreter for Prolog, which I'm going to talk about next. And we'll be using Prolog to write an interpreter for Lisp. So, that's going to be quite challenging. Okay. Or at least more challenging than the other assignments I have in mind for you. Okay. So you get this error. Because it can't type correctly the signature. It can't find a proper signature for high final pass. Okay, it just sees this inconsistency. Okay. Yes.
Why does the operator assume the two arguments are integers?
Because less than equal to in ML is only defined between integers. It's not defined between strings, at least. If it was, it would be in trouble. If it is defined between int and string, it would be in trouble.
Would it cause confusion between float and those?
Between floats and integers?
Yeah.
So let's not get into these little details. The point is that a string and an int can't be compared, right? So there are applications of less than equal to that don't make sense. Do you agree with me there? If you agree with me there, then I can always make a call that's inconsistent. And if it is, then I'll get a type error. That's the point. Let's not get into floats and ints and, that kind of stuff. Okay? And casting.